In this video, we're going to explore another way of looking at limiting reactant problems. We're going to problem solve these by using what we call a RICA table. RICA stands for reaction, initial, change, and after. And so in these tables, we start by filling in our chemical reaction that we're actually looking at, our balanced chemical reaction. And so we'll just start with a very generalized reaction of A plus 2B yields 3C plus D. And so there we have our reaction to start with. Next, we're going to fill in the initial starting amounts we have of our reactants. These amounts are always going to be in moles. Some would say that we have to be in the mole hole in order to perform these problems. And so be sure that you're converting all of your starting amounts to moles for this type of analysis. And so in this general example, we're just going to say that we're starting with an X amount of A and a Y amount of B. Note that at this point, we are not taking into account our stoichiometric ratio. We will take that into account later, but for now, this is simply the number of starting moles we have based on our amount of grams. Initially, we don't have any product, and so we can fill in zeros for the amounts of our starting products. At this point, we would want to determine what our limiting reactant is. We'll go over how to do that later on in the video, but for now, let's assume that we have conducted that analysis, and we have determined that our limiting reactant is A in this reaction. Remember that a limiting reactant will be completely used up over the course of a reaction. And that means that the amount of A that we have after the reaction is over is going to be 0. So we can fill that in now. Which brings us to thinking about the change. How much are each of these substances going to change throughout the course of this reaction? If the amount of A started with an X amount, and we have 0 of that left after the reaction, then the change in A must be equal to minus X. We're going to lose an X amount to be left with 0. Now remember that we have determined that A is the limiting reactant, which means that all of the other changes in this reaction are going to be based off our change of A. That's a key point for limiting reactant problems. A is our limiting reactant, and so all amounts are going to now be based off the amount of A. Now we are going to take our stoichiometric ratio into account. For every 1 A that we lose through the course of our reaction, we also lose 2 B's. And so the amount of B that is going to be lost will be equal to minus 2X. We're going to lose 2 B's for every 1 A that is lost. And likewise, the amount of C that we gain is going to be equal to 3 times X. And we have a 1-to-1 ratio between A and D, so the amount of D formed is going to be equal to, or the amount of change in D is going to be equal to plus X. Now we can fill in our actual after amounts. We started with Y amount of B. We lost an amount equal to 2X. Therefore, the amount of A of B that we have after the reaction is going to be Y minus 2X. Likewise, our amounts of C and D are going to be 3X and X, respectively. And so this was a very generalized example. Let's look at this in action. We've seen this example a couple different times now. Our 10 grams of gold and 10 grams of chlorine reacted together to produce gold-3 chloride, and we want to know what the limiting reactant is, how much gold-3 chloride will form, and how much of our excess reactant is going to be left over. Now we're going to approach this problem using a RICA table, though. And so our first step is just to set up our table, our reaction, initial, change, and after. Our next step is we need our balanced chemical equation. And so our balanced chemical equation, when we start to put that together for this reaction, we know gold is one of our reactants, chlorine is our other reactant. Chlorine is a diatomic, so AU plus Cl2 forms gold-3 chloride, which will have a chemical formula of AuCl3. And now we have to balance our reaction. We can see that we have 2 chlorines on our reactant side and 3 on our product side. So we're going to need to double our amount of gold 3 chloride for 2 AuCl3. Which means we'll need 3 Cl2s and 2 Aus. Now have our balanced chemical reaction to go into our table. Our next step is to calculate the initial number of moles we have using our starting amounts of grams. And so we know that we have 10 grams of gold and 10 grams of chlorine. And so we're going to use our molar masses to convert both of those amounts over to moles. For a starting amount of 0.0508 moles of gold and 0.141 moles of Cl2. And so we can fill those amounts in our table. And we know that we're starting with an initial amount of 0 for our product, our gold 3 chloride. And so now we have our initial amounts of all of our reactants. Our next step is to determine our limiting reactant. To do this, what we want to do is choose one of the reactants and figure out how much of the other we need based on the starting amount of the one that we choose. And so for this example, let's go ahead and calculate the number of moles of Cl2 that we're going to need to react with all of the moles of gold that we have present. We said that we're starting with 0.0508 moles of gold. We can see from our balanced chemical reaction that we need 3 moles of Cl2 to every 2 moles of Au, which tells us that we're going to need 0.0762 moles of Cl2 to react with the 0.0508 moles of Au that we have present. And so again, we need 0.0762 moles of Cl2. When we compare that to the number of moles of Cl2 that we actually have, we have 0.141 moles of Cl2. So we can see that we have more than enough Cl2 to react with all of the gold that we have present. This means that gold is going to limit our reaction, and Cl2 is in excess. Cl2 is our excess reactant. And so since gold is our limiting reactant, we can fill in a 0 amount for the after for gold. We're going to have 0 left because it is our limiting reactant, and it will all be used up. This means that we know the change in gold must be minus 0.0508. We can then use our molar ratios to find the change in moles of our other substances. And we find that Cl2 will change by 0.0762 moles. Note that this is a reaction or a calculation that we've actually already done. And our AuCl3 will change by an amount of 0.0508 moles. And so we can fill those into. We're now ready to calculate the amount that will remain after the reaction is complete by simply doing the math. 0.141 minus 0.0762 leaves us with 0.0648 moles of Cl2. 0 plus 0.0508 leaves us at the end with 0.0508 moles of AuCl3. Now we can use these molar amounts that we've calculated that we will have after the reaction and our molar mass to calculate the actual number of grams of AuCl3. And we find that we're going to create 15.4 grams of AuCl3. And we can do the same thing with our amount of Cl2 that remains. And we see that 4.59 grams of Cl2 will remain after the reaction is complete. Now we can do a quick check, because we know that we're going to form 15.4 grams of AuCl3, 4.59 grams of Cl2 actually remains. We add those together, and we see that after the reaction is complete, we have a total of 19.99 or approximately 20 grams, which was equal to our starting amount of total reactants. And so that's nice, a nice little check to do at the end to make sure that those amounts add up, because the law of conservation of mass tells us that they have to. We just have a small difference due to rounding. Let's look at another example. In this example, 90 grams of barium nitrate and 50 grams of sodium phosphate react to form barium phosphate and sodium nitrate. So again, we want to know what the limiting reactant is, we want to know how much barium phosphate will form, and we want to know how much of our excess reactant will be left. So our first step is writing out our balanced chemical equation. And we can see that here. So here's our reaction. If you make sure, I would pause the video now to make sure that you are able to come up with this same reaction. That is an important skill. Next, we can calculate our initial number of moles based on our starting amounts of both of the reactants. And we see that we're starting with 0.345 moles of barium nitrate and 0.305 moles of sodium phosphate. And so we can add those into our table. We also know that we're starting with 0 moles of our products. Next, we're going to find our limiting reactant. To do that, let's determine the number of moles of sodium phosphate that are necessary to react with our initial amount of barium nitrate. So we know that we're starting with 0.345 moles of our barium nitrate. And if we look at our molar ratio from our balanced chemical reaction of sodium phosphate, for every 3 moles of barium nitrate that we start with, which give us 0.230 moles of sodium phosphate necessary to react with our initial amount of barium nitrate. So given the amount of barium nitrate that we have to start, we need 0.230 moles of sodium phosphate. We have 0.305 moles of sodium phosphate, so we have more than enough of the sodium phosphate to react with all of the barium nitrate. That means that barium nitrate must be our limiting reactant, and sodium phosphate is in excess. So now, since we know that barium nitrate is our limiting reactant, we know that we will have none of that left after our reaction, and so we can fill in a 0 there. That allows us to now fill in a change of our barium nitrate of minus 0.345 moles. And we can fill in our other changes, once again taking our stoichiometric ratios into account. Our limiting reactant is barium nitrate, so all of our changes will reflect the amount of barium nitrate that is lost. So 0.345 moles of barium nitrate times our molar ratio relating to sodium phosphate tells us that we're going to lose 0.230 moles of our sodium phosphate. Now again, remember that's a calculation that we have actually already done. And then likewise, we're going to do the same using our molar ratios of barium phosphate to barium nitrate and sodium nitrate to barium nitrate. When we do that, we have changes of 0.115 added for barium phosphate and 0.690 added of sodium nitrate. If you did not find those numbers, go back and check your calculations. So we now have our changes for all of our substances in our reaction, which means that we can fill in our after amounts. And so we're going to be left with 0.075 moles of sodium phosphate, and we will have 0.115 moles of barium phosphate and 0.690 moles of sodium nitrate at the end of our reaction. Finally, we can use our molar masses to calculate the amount in grams of barium phosphate that is formed and the amount of sodium phosphate that is left over. And hopefully some of you caught my slight error in my chemical formula here. That should indeed be Ba3PO4 But we perform our calculation, and we see that we're going to form 69.2 grams of barium phosphate, and we'll have 12.3 grams of sodium phosphate left over. Which were the final calculations that we were actually looking for. And so generally speaking, I hope this has been helpful. This use of a RICA table is a great problem-solving tool when it comes to limiting reactant problems, because it sets you up with all of the information that you're going to need. Just take a note, for those of you using Chem 101, that it will look a little bit different, but it's still the same exact type of table. We have our reaction here up top, so this would be our reaction here. And then instead of initial, they just use the terminology of before, and then change and after. But it's still the same exact thing. Reaction, initial, change, after. So still the same exact process. Again, I really hope this has been helpful. As always, if you have any questions, don't hesitate to reach out.